But the reason we are here is the book club. For those of you who haven't been before, this is not our first book. We went through the Rust programming language, which is like the de facto book on Rust. You kind of think of it as the documentation for Rust, but not exactly. It's kind of more just explaining how to use the language. We also went through Atomics and Locks, which we finished just before Christmas, which was amazing. If you haven't read it, I'd highly recommend it. You can buy it. It's fantastically written. We did a vote for what book to do next, and Rust for Rustaceans was the winner. This is an idiomatic program for experienced developers. It's a really nice next step in Rust learning, going into a bit more than just how the language works, but actually how to write good Rust beyond just writing any Rust. Yeah, this is diving a little bit deeper. The first 5 chapters are like foundations, types, designing interfaces, error handling, project structure. And then moving on to testing, macros, asynchronous programming, unsafe code, concurrency and parallelism, form function interfaces, Rust without standard library, and the Rust ecosystem. So there's a lot of stuff coming, but it's all good stuff. And it builds up well. The premise of the book is that you can read the first 2 chapters and then you can tackle the other chapters in any order. For simplicity, we're just going to tackle them in the order that they are in the book. If we run this in a way that we try and get as many different people to do chapters as possible. So if you've never done a talk before, I would really, and you would at all consider it, please let us know and volunteer yourself to take a chapter, because it's a really great way to dip your toe into presenting and speaking, and it also forces you to absorb the content more than you would if you just read it just for yourself. You don't have to be an expert by any means. Like I said, this isn't like doing a conference talk where you feel like this is a safe environment for everyone. It does get posted to YouTube after, but again, it's not demonstrating itself as saying this is the de facto thing. It's a book club, so it's a really nice introduction to it. So please do get in touch if you would consider taking a chapter and you don't want to hear just mine and Matt's voices for the entire time, and probably Tim's. If you want to diversify the presenters, then please do. If you don't have a copy of the book, No Starch Press is the publisher. You can buy it direct from there, or you can also get it from your local bookshop or Amazon. Libraries around the world are normally pretty good with books. Even if they don't have a copy, they can normally get one in. So if you don't have a copy and you want one, you should be able to borrow one somewhere. But without further ado, let's get started with chapter 1. Chapter 1 is foundations. We're going to cover memory and variables, ownership, and borrowing and lifetime. So these are all topics that we've covered in some capacity, but this is setting it up for the rest of the book. So it's going to be describing it how Jon describes it in the book and how to think of it in order to get the most out of the rest of the book. The first thing we kind of get introduced to is thinking about the virtual memory address space. So this is kind of mentioned in passing, but just for context, the stack is for local variables and function data. The heap is for dynamic memory allocations. Then you've got BSS for uninitialized data, which is all zeros when the program's loaded. You've got the data segment for global and static variables, and then the code segment and text segment, which contains code for the program and usually possibly some static strings as well. Got this lovely diagram from the MIT OpenCourseware. It's a really nice visual representation, so you can kind of think of this as, this is how the memory is being laid out, this virtual memory. In the low address space, you've got the text segment, data segment, BSS, and then the heap growing up, stack growing down. That's the mental model you can have to start with. It's not crucial to have at this point, but it's nice to have for going forwards. Other memory that you might have access to that Jon mentions is memory mapped registers. So mapping hardware registers into virtual memory, and memory mapped files. So this is mapping a file into virtual memory using, for example, an mmap system call. I think maybe Chris Light did a talk a little while back where he did this between a C++ program and a Rust program. I have a vague recollection of that. If anyone remembers, then let me know. And then also, non-volatile RAM, so RAM that retains data without power. That's kind of all we're going to mention on that topic for now, anyway. The main thing we want to get out of this kind of start is the terminology. So when Jon in this book says value, he's meaning a type plus an element of that type's domain of values. So for example, 42 is an integer and it's one of the valid elements in the domain of integers, whereas like 42.5 would not be a valid integer. The representation is how you would store that value in bytes, so that will depend on how you choose to store it. And as the developer, you often don't have to think about that. Sometimes you do. We've done talks in the past about the like fast square root and some of the kind of things you can do, which isn't actually that fast, but yeah, there's benefits to understanding how it's actually represented in bytes. So that's the representation. A variable is the named value slot on the stack. So we say we're declaring a variable, that's the named value slot on the stack where we might put that value. Place is a location that holds that value. So for example, a variable is an example of that, but it could also be something on the heap. And a pointer is a value that holds the address of a region of memory. So it points to a place, and then that place might have a value in it. So in this example here, X is a variable. The value in the value slot place of that variable is an I32, 42, as kind of mentioned earlier. And here, Y address 1 is a variable, but the value in the value slot place of that variable is a pointer. And then that pointer points to another value, which in this case is 43. And that value, if you actually tried to print it out as a pointer address, would look like something like this. So going a bit further in variables, you can think of it, Jon introduces this idea of a high-level model and a low-level model. The high-level model is just that a value is named by a variable, and accessing that value draws a line or dependency flow from previous accesses to a new access. So this is kind of interesting mental model to introduce. So in this case, you start off with you have this let mut x, which is declaring your variable, but at that point you don't have a value, so you can't draw a line from it yet. When we set that value to 42, we can then start drawing lines from it. We can flow from x to y using ref x there, and then we can access y. If we try and then have setting x to 43 because it was mutable, we then are going to get an error if we try and access y again, because we've drawn an access line from the y down to, so from this print line y back to where we actually originally got it, and that's crossing our mutable access. So it's a slightly interesting model. I tried to draw it to try and introduce this idea of flows. Apologies for my drawing skills. You're starting off with x equals 42. I've just started it from the point at which we can start drawing lines, which is once we actually have a value. Then we have this immutable access, and every time we access it, we have to draw a new line back to where we accessed it. Seeing those lines going backwards rather than forwards is sometimes helpful. If we stop at this point, that print line prior to modifying it, then everything's fine, because there's no the mutating is happening after we've finished our immutable accesses. There's no crossover there. Whereas if we then accessed it to do another print statement below, you can think of that as crossing, because we're doing that. We have to draw a line back to our previous access, and that line is going to be kind of intersected by this mutable access. So maybe that diagram's helpful, maybe it's not, but that's how I was kind of visualizing the flow that he talks about in the book. And we're not talking about lifetimes yet. We're not talking about that comes later, but this is just talking about this kind of these kind of flows of accesses. Then you can go into what he calls the low-level model of the variables. So variables name memory, and that memory may or may not hold a legal value. So for example, on the first line here, let x is an I32, we haven't actually given x a value, but it still has an address. So even though I'm not assigning the value until later on the fourth line here, if you print out the addresses, you'll see it goes the first one, x, then y, then z, even though at the point at which I declared x, it didn't have a valid value in it. Now, Rust won't let you access it until it's been assigned, but the memory address still exists. You know, you've still declared that variable. So moving on now to memory regions. Again, going back to that diagram from earlier, this is the kind of model to have in your mind. So the first thing to talk about is the stack. So when a function's called, a stack frame is allocated onto the top of the stack. And that stack frame is a block of memory containing parameter values, return address, and space for local variables. When a function returns, the stack frame is going to be popped, and the stack pointer is restored to the frame pointer. But the old stack frame memory might still stick around until it's overwritten. But variables stored on the popped stack should not be accessed because they could be overwritten. So that's where this concept of lifetimes becomes really, really useful. Conversely, when you're talking about the heap, that memory isn't tied to the current stack frame. It's explicitly allocated and deallocated or freed. And if you don't deallocate that memory, you're essentially leaking, which might be deliberate, probably by accident. And pointers to the heap addresses can be passed around so that you can then access that memory. There's also this idea of static memory. So in this case, we've declared a static memory region with static X, and you might remember this from chapter 1 of atomics and locks. Static memory is something that you can then pass into a spawned thread because it's going to live long enough. So even if you never do a join on that thread, you know that the data that you've passed in is going to live long enough, so the thread's allowed to access it. There's also this idea of static lifetime. So any static data that we declare like this has a static lifetime. But static lifetime means that the data lives until the end of the program. It doesn't necessarily have to have been created with the program, and it doesn't necessarily have to live in the static memory region in Rust if it has a static lifetime. So we can leak memory to create it, but that memory will be on the heap rather than in this static memory region. So in this case, we're saying, okay, give me this static reference I'm going to do box new in order to do my allocation on the heap, and then I'm going to leak that memory to get my static reference out. Now, just like before, I can spawn a thread and I can access it on that thread. I'm not suggesting you write this code, don't write this code. But this is just to introduce the idea. There might be some cases where you need to, for example, if you've got a big data structure that's going to live for the whole program anyway, and you want to just make it static, this is a way you can do that. But obviously, it's going to live for the duration of your program. So you may or may not want that. One thing that Jon mentioned at this point is, what about const? So const is computed at compile time, and any access in the code are replaced by the calculated value at compile time. So it doesn't need to live in the static data memory. The next topic that we kind of move on to, actually, sorry, there's a chat's going. Any questions or anything? Do you think we need to break? Or... Yeah. Yeah, go ahead. Any questions? All right, I'm going to assume that everything is fine in the chat and check it out at the end. Let's plow on with ownership. So in Rust, you have this idea that all values have a single owner. And one single location or scope is responsible for any deallocation that needs to happen. When you assign to a new variable, you move that ownership. So in this example, you're saying let value equal, and then some type, some value of that type, some instance of that type. And then I'm saying let value 2 equal value 1. So I'm moving it, the ownership, into val 2. And at the end of this little scope bracket here, it's deallocated. So if that value had some data that it owned, that would be dropped. And we wouldn't be able to use the original data, that val 1. Types which implement the copy trait are not considered moved by an assignment. They're considered copied. So assigning to a new variable, instead of moving the ownership, copies it. So in this case, we've got some copyable type. We copied the value 2. And then although value 2 goes out of scope, v1 is still in scope. So we can still access it. This is a mistake on my part. It copies. When it comes to heap allocation, this single ownership model prevents the dreaded double delete. So this is the idea that you have some memory that you've allocated on the heap, you want to deallocate it, but actually it's already been deallocated. So that's what's called undefined behavior. What might happen is you might crash your program, you might delete something you don't expect to delete. Lots of bad things can happen. In this case, we're saying let value 1 equal box new 42. That allocates the I32 on the heap. we're then going to move the ownership into value 2. And then when value 2 goes out of scope, box is dropped using the drop trait, and the I32 is deallocated on the heap. If value...
Hi. So I have a question here. So
Yes, yeah.
I'm new, so this will be a kind of a beginner question. So please don't mind. So when we declare a value one outside this block, and then we assign value two to value one, uh, why is it getting why the ownership is getting moved to value two? Just because it's allocated on heap and it is a pointer, and pointer assignment makes it by default moving the object to another pointer. Is that the reason?
Yeah, I guess it's good to think about the consequences if you didn't do it. So if you said that value, so someone has to deallocate this memory, right? If you allocate the memory, you have to deallocate it. So how do you ensure that it only gets deallocated once? And the way that Rust does that is it introduces this idea of moving ownership. So what's happening is instead of value one being responsible for deallocating that I32 on the heap, value 2 is now responsible. And it's kind of an aspect of the borrow checker that means that value 1 is considered an invalid reference. It cannot be used. It won't allow it at compile time.
So other way could also have been done. So suppose we own concept of single ownership is nice. So suppose let's say that value one is the owner and value two uh, is because it is being okay.
Sorry, I've just muted them. I think they didn't realize they were unmuted.
Okay. Why value one being a single owner would not work? That's my question.
So if value 1 was the only owner, then you can still access it anywhere. But here, by doing an explicit assignment, I'm moving the ownership. If I just wanted to look at the value, I could look at a reference to it. I could dereference it and copy out the I32 itself. But this syntax means move, essentially, is what you should think about it. Is that syntax, whereas previously you might have thought it as meaning copy, and in cases where it's copyable, it does mean copy. But in the case in just default vanilla Rust, whenever you see an assignment like that, you're moving it. Does that make sense?
Okay, and yeah, it makes sense. And if it was not, if value one equal to 10, if that was the case, will that also mean that value two is moving?
If it was just an I32, because I32
Yes.
implements copy, it would be fine because it's one of the special cases where it implements the copy trait. The way I tend to think about this is well, for simple types, you can think of it as like I'm just copying the stack data.
Okay. Perfect. Okay.
Now, because in special cases, that stack data might still not be copyable. Like, for example, maybe it is secretly a pointer and it is in charge of deallocating in some capacity. Maybe there's some reason why you shouldn't copy this data. When you create a data type, it won't by default implement the copy trait. But in reality, probably for a lot of stuff, you can just implement copy and then those assignments will be fine. But in any case where you're doing a heap allocation, especially, or you've got some other behavior that needs to happen when it goes out of scope, like closing a file handle, that's when it becomes really useful to have this move by default. And if you're coming from a C++ background, you're probably familiar with using std move. The other nice thing is like now we're using move by default, so you don't have to write std move anywhere. You're getting that efficiency right out of the box. In the case of simple types like an I32, you might not see why. You might be like, why can't I use my case? But you can because it implements copy traits. So it's only when you construct like a slightly bigger object that you have to auto-derive copy, which you can do on anything that doesn't implement the drop trait, which I think will come on shortly. So
perfect. Thank you so much.
No problem. So types that implement the drop trait can never implement copy. And that's for all the reasons that we just talked about, like who is going to do the drop? The drop can only be done once. Someone's got to do it. And this single ownership concept means you need to know who is actually going to be dropping that data. If you want to share that data, rather than doing that assignment, you would lend the value using a reference. And references are just special pointer types. There are two types of references in Rust. There are shared references, where you can have multiple instances of them. and there's mutable or exclusive references. If you did the Atomics and Locks book club, you'll know that the preference is for referring to them as exclusive references, because shared references can be mutable, as we'll come on to later. So it's good to think of it as shared references and exclusive references. With shared references, the compiler can assume the value that it points to will not change. And that means for multiple accesses, the compiler could read the value once and then reuse it. So for example, here, if I have a function that's doing something with an input reference, I can read it once and then I can read it again. And the compiler knows that they will always have the same value. The underlying value of the input is not dropped because we never actually transferred ownership into this function. We just lent it to the function using a reference. With exclusive references, the compiler is allowed to assume that they are the only thread with access. That's this idea of exclusivity. And no other references are going to be aliasing to it, because it's not just that you can only have one exclusive reference. If you've got an exclusive reference, there are also no shared references as well. And that enables optimizations because you can assume that none of them are aliasing to it. You can reorder things that you wouldn't otherwise be able to reorder by virtue of the fact that you can assume any other references in that scope are not going to be referencing the same underlying data. There's an important distinction between a variable which points to a reference being mutable and the reference it holds being mutable. So in this example, we're declaring a mutable variable x and assigning 42 to it. We're then taking a reference to it, specifically a mutable reference. Because we've got a mutable reference, it means we can modify x through the reference that we have. And here we're printing that value now, it's 43. But the value ref itself is immutable. You can see I haven't put let mutable value ref equal ref mut x. So value ref is immutable, but the data it references is mutable. And you can compare that to, for example, or using the same example actually. So again, we've got this mutable x, we're setting it to 42. We've also got this additional mutable y that we set to 1. Now, we're again getting an immutable value ref and setting it to mutable reference to x. But we can't reassign this val ref because the val ref itself is immutable, even though the data it's referencing is mutable. So it's a like slightly subtle distinction, but it depends on what the binding is. So you get a nice error if you ever make a mistake on this. Cannot assign twice to immutable variable val ref. Our variable is val ref. That's the thing that we can't assign to twice. That doesn't mean we can't modify the data inside it. As we did in the previous case, you can see here we were able to modify the data inside it to 43, but we can't reassign what it's pointing at. So it's a subtle distinction that's good to have in your mind. And we can compare that to if we took a mutable val ref and then we took an immutable reference to x. So x itself now, the reference that we have to x is immutable. We cannot assign to x through this val ref because the reference we have is a shared reference or immutable reference. So we cannot modify x through val ref here, but we can modify the variable itself, our val ref, by instead of pointing to x now, it's pointing to y. And that's totally allowed because the binding that we have there is mutable, even though the thing it's pointing to is immutable. So it's a subtle distinction. If it doesn't make sense immediately, just read the examples again, play around with Compile Explorer. It does make sense. But yeah, pay attention to where your mute is because it does matter. When you have a mutable reference, you always have to leave it in a valid state. You can still take ownership of the value, but if you do that, you have to leave a valid new value in its place so that the calling code still has something to call drop on. And the way you can do that is replacing it with a default type using stdmem take, or you can exchange it with some other T using stdmem swap, and that leaves the original owner something that it can drop. So again, you can think of this as like I'm swapping the stack memory. It will be the classic example. So it doesn't know that it doesn't have the same data underneath, and I've still left it in a valid state. but I have kind of taken ownership of the thing inside. The next topic to talk about is interior mutability, and this is where it becomes really helpful to have referred to it as shared references and exclusive references, because when you're dealing with a type that has interior mutability, you can mutate the data using a shared reference, even though that shared reference is not a ref mute, it's just a ref, but it's a shared reference. And if the thing has interior mutability, that means I can change it. In order for that to work, you only have interior mutability on types that provide other mechanisms for giving the safety guarantees that we need to give in order to ensure that our program is fully memory safe. One example is a mutex. So if we have a reference to a mutex, well, the mutex is going to guarantee exclusive access with a lock. So if ever I try and modify the data, I'm going to have to lock it. Therefore, I can guarantee that at that point, when I'm modifying the data, I must have exclusive access, which is one of the things that we need. With a ref cell type, that can't be shared between threads. It can't be moved between threads because it can't be shared between threads because it's not sync, which means you can't pass a reference to a ref cell. And when you borrow with a ref cell, it's tracked at runtime, which means you can still run into problems at runtime, but they won't manifest as memory safety vulnerabilities. It might manifest as a crash, or it depends on how you use it. You can totally use ref cell completely safely if you're using it carefully. But yeah, there are these types that have interior mutability. And again, you might remember from the Atomics and Locks book, you can think of, and wherever else you've been reading it, that an arc has interior mutability on the reference counter itself. So even though it doesn't provide interior mutability directly to the T inside it, unless you've got a type that has interior mutability, it technically has interior mutability because you do modify the ref count in order to be able to increment and decrement to figure out how many references you have. Okay, so next topic is lifetimes. You can think of a lifetime as a region of code that a reference must be valid for. And the compiler is smart enough to kind of figure out like branches. So in this case here, we have a mutable X, and then we take an immutable reference to X. Now, that is okay as long as we don't modify X in a branch that crosses our immutable access of X. So in one branch, we are modifying it. If we take this branch, we cannot access R anymore. We shouldn't be allowed to access R because this is a shared reference and this would be using the mutable reference or exclusive reference. So if I tried to access using the shared reference again later, that would error. Whereas I can access it here because these two branches don't cross. So you're either in one or you're in the other. Therefore, it's acceptable. If I draw a line back from this access of R to this assignment of R, there's no mutable accesses between those two. So it's acceptable to do this shared reference access. So if I had uncommented that line, then I would have gotten an error like this. You cannot assign to X because it is borrowed. X is borrowed here, and X is assigned to here, but it was already borrowed. But without the second print statement, the borrowed checkers allow the code thanks to non-lexical lifetimes and this idea of, drawing these paths of like, can I get back to where I received this reference without violating any of the conditions? And that means you can also do this thing where you patch the holes 3 times. I'd never come across this before. It's really neat. This example is straight out of the book, as a lot of these are. So here I'm saying let mutable X equal box new 42. And then I'm saying let this mutable Z, which is a reference to X, let mutable Z equal a reference to X. Now, this print statement, this first print statement is valid because between this access and this assignment, X is unchanged. So we had access to it. There were no exclusive accesses at that point, so that one's allowed. We then make use of our exclusive reference, which was this mutable reference up here, to modify it. So now Z's reference cannot be accessed because there was a mutable access, which means my my Z is invalid. But I can reassign Z after to get X afresh, and now it's valid up until the next time I access X and try and modify it. There's a slightly funny merry dance that's happening here, but the end result is that I do have Z at the end because X was not modified since the last assignment of Z. So if I draw a line back from here, I can get to this one. And if I draw a line back from this one, I can get to this one. So, or if it's actually the second round of the loop, I can get back to this one. So it's basically able to like patch these holes with reassignment. The ref X assignment to access, that those accesses must not overlap the modifications done through the ref mutable X. So it's a slightly funny concept, but it does make sense thanks to this kind of reassignment. Okay, the next topic is generic lifetimes. Generally, as an advice, you kind of want to avoid having more than one generic lifetime if possible, but sometimes you do need more than one. So this example that Jon gives is you've got a document which will live for some lifetime, and then there's a delimiter that might live for another lifetime. And there's no reason why those need to be related. Your delimiter could be a temporary, your delimiter could be static, your document could be, could be static, or it could be data that's passed in. Like there's no reason why those two should be related. And if you tied them together, you would get yourself into an annoying case where you cannot use certain delimiters, even though they don't need to live any longer than you're using them for this split operation. You would still be enforcing them to live as long as the document accesses themselves, which you don't want. The kind of last big topic that kind of ties into that is this idea of lifetime variance. So a lifetime, for example, A, would be considered a subtype of B if it lives at least as long as B. So static, for example, outlives A, which means that static is a subtype of A. And that then leads on to the final kind of concept that he brings with, which is covariance, invariance, and contravariance, which were not concepts I had come across until I read this chapter. With covariance, that means you can use a subtype, so something that lives at least as long as it in the case of lifetimes, in place of the parent type. So you can pass ref static string slice to a function which takes a ref tick A, which is a generic lifetime string slice. And just to show you what that would look like in practice is if I have a slightly flipped the example here. So instead of using a vec here, I'm just using the value itself. So even though I'm using a single lifetime parameter, this tick A, when I actually come to use it, they're not actually the same lifetimes. I've got this value here, which has some lifetime. I take a reference to it, which is going to be my reference here, tick A. I then construct a vector and put a vector with that lifetime tick A in it. So this vector now has this lifetime tick A. When I come to actually use this method, the second parameter I'm using is not actually, it doesn't actually have the same lifetime as this string here, because this one I've done toString and then taken a reference to it, which is slightly different. We're doing astra here. Whereas this one is actually a static string. So, but because static is, if you remember, a subtype of A, it outlives it, I can pass this in fine, because this type of function signature, or this type of parameter, a reference of T, allows for covariance, which means I can pass the subtype in place of the type. It's slightly interesting concept, but really, really useful, especially when you then move on to other cases. But the general premise is if it outlives it, you can use it in this case where you're passing a ref T. There is, however, cases where you've got invariance, which means you have to pass the exact type And that happens quite often when you're dealing with mutable references. So in this case, I'm passing a mutable reference to a vector of static strings. I cannot pass one of these in place of a tick A string. So here I've got exactly the same function signature, but when I'm actually calling it, I'm kind of using it in reverse. In this case, I've got a vector of static string slices. Now this one here is a static string slice, so I can add that to the vector, no problem. If I allowed any generic tick A to go in here, and then I said, oh, okay, well, this one is a subtype of, static is a subtype of A, so I'm allowed to substitute it. If I allowed that substitution, that would mean that I could end up referencing memory way beyond when I'm allowed. In this case, I've got this value and then passing a reference to it. So this would have some lifetime tick A, whereas this vector is a tick static. That's what I created. So even though this is a subtype of tick A, I'm not allowed to substitute it in. This will error. And the error is going to look like this. Value doesn't live long enough, which makes sense. The type annotation requires that the value is borrowed for a static lifetime. This declares the value here, and the reference to that value does not live long enough. This is not a static variable. This will only live for its scope. And that means that the value is dropped while it's still borrowed. So that's kind of, powerful concept, and it goes on to a nice example later, well, very, very soon. The next thing to think about is contravariance, which is just where things kind of are slightly the reverse of that. It's where you think of it in the case of function arguments. Function arguments are most useful if they have loose restrictions. If I force a parameter to be static, that means I can't pass in anything that lives less than that. So if I wanted to, for example, in the delimiter case where I'm trying to split a document on some delimiter, I shouldn't make that delimiter be static because there's really no reason for it to be static. Instead, I should use a generic lifetime. I should choose the kind of parent type rather than the subtype in order to allow as many things as possible to be passed in and make this function as useful as possible. And if you can get your head around that concept of variance, it helps you make good lifetime choices about when you can have two lifetimes be related and when they should be separate. And this example, again, straight out of the book, there's this mutable string slice type, which is taking a mutable reference to a reference to a string slice. Slightly wordy. In this case, I'm saying let mutable s equal hello. And then I'm saying construct a mutable string slice and modify the inner value. But then this is just a temporary, so it's just going to drop anyway. The lifetime of this reference here is going to be determined depending on s. And the lifetime of the inner string slice is, in this case, static, because this is static string slice. And that means that I can still access this s here, because the lifetimes are totally untied. And it might not be obvious why this requires two lifetimes, which is why it's really, this is kind of why he's mentioning this whole idea of variances. So you can understand why this would error if you just used one lifetime. So we're taking exactly the same example, but instead we're using the same generic lifetime parameter for both references. And in this case, if we try and do the exact same thing, we get an error. And the error we get is that there's a mutable reference that's still alive, which is wild. You're like, what mutable reference? There's only one reference lifetime here. And it's invariant because it's this, we've got this ref tick a mute. So because it's this mutable reference, we have to, we can't substitute a different lifetime for it. And that means we have to treat both references as if they're static, which means it's as if, because this reference was static, that means this reference is static, even though we know this lifetime is not not static, but the compiler has to treat it as static. And as a result, it's essentially like we have created a static mutable reference, which means we can never use any of our immutable references to it, or any of our mutable references for that matter. And adding curly braces and introducing scopes won't help. This is fundamentally the problem is having these two lifetimes that are unrelated being linked together by our struct definition. And the error we get is that we cannot borrow S as immutable because it is also borrowed as mutable. And it's saying that this is the mutable borrow here. But like I say, we shouldn't still have this as a mutable borrow because we're not using it anymore. But because the lifetime has to be static because we've bound these lifetimes together, that means we get an error. And that's due to the invariance of the fact that it was a ref mut t. If it had just been a ref t, wouldn't have been a problem because ref t has covariance, which means you can substitute a shorter lifetime, but you can't do it with ref mut t. So the compiler has to treat the mutable references we took as if they're still live because they're static. So that invariance reduces the flexibility and means that in some cases, you're going to have to introduce multiple lifetimes, which can complicate things, but is sometimes needed to maintain covariance across types. Which, yeah, all of this was new to me. I hope I've understood it correctly enough to explain it to you, but yeah, please read the chapter for any clarifications. Just to summarize there, because that is the end of the chapter, we talked about variables versus values. We talked about memory regions, ownership, the borrow checker, and this idea of covariance, invariance, and contravariance. So very interesting chapter overall. So yeah, that's the end of chapter 1. Shall we do like questions, chat? I haven't opened the chat yet, so I'm just going to have a look now. But if anyone has anything they want to, yeah, shout out or any thoughts they had about the chapter, if they were able to read it, then yeah, please feel free to just shout out. No questions so far. Okay, someone in the chat said contravariance allows you to pass a generic lifetime. So contravariance is just the idea that you want to provide the loosest restrictions that make sense when you're defining a function, is my understanding of that. Because if you do too tight a restriction, you're going to end up restricting cases that would otherwise make sense. So it's kind of, yeah, contravariance. Someone says those are terrible names. Contravariance, yeah, just the names the names I was given. I'm guessing they probably have history and meaning in academic contexts, and that's why those names were chosen. Oh yeah, someone says you can show elided lifetimes in your editor with Rust Analyzer. Yeah, very true. And types as well. It's really useful to sometimes view the full types in certain cases because a lot of it does get hidden away. Okay. Any questions at all?
Hi, Ciara.
Hi, Richard.
I just wanted to say thanks for going through all that. I'm not sure I got every detail of the different sorts of variants, but I think I got the gist of it enough to know what I'm looking for now when I get those errors. Even while you were describing it, it did sound to me a bit like the more traditional errors we used to get in C++ when you're trying to do return functions at different levels of an inheritance hierarchy, where they've got different return types, and it starts complaining you can't have covariant return types. They've all got to be the same return type. Whether that's the same sort of meaning of covariance, where you've got this sort of subsetting and supersetting of types in an academic context, like you were describing. Because you've got the sort of traditional idea, like you said, that you want the inputs to be as generous as possible and the outputs to be as strict as possible so you can use it in a wide range of contexts. And gist I got from Rust was that, yep, they've taken those concepts and they've run with it, and they've made sure it's formalized, and they've got the several different varieties, and prepare to have to think through it carefully when you're working with them. But it'll all be nice and safe when you do.
Definitely, and you're exactly right. And in the book, Jon actually does talk about introduces the concept, talking about types beyond lifetimes. I think I just launched into lifetimes, but maybe it would have been useful. I'll try and find the.
I would say that the whole reason for lifetimes in the first place is to stop one single thing from going wrong, and that is having a reference to something that doesn't exist anymore, either because it's just been deleted or it's been moved. And the whole point of lifetimes is to stop that, because that's a huge problem in C and C++, where you have a pointer to something and you delete it, but you still have the reference hanging around, and you get a dangling pointer or null pointer exception error, right? And that's the main thing you've got to remember with lifetimes to help you through the error messages, I find.
Yeah, I entirely agree, Matt. I'm not going to defend the risks we run with C++. Although, in fact, I would say that the memory lifetime isn't the biggest problem I've faced. The one that hits more often is functions taking const references that they assume are const, and not realizing that other functions that are simultaneously alive and accessing that can happily be changing that under your feet. And so it's more that it is alive. It's just you're not very clear on who's owning it and who's respecting the current value of it. The aliasing is basically out of control, whereas Rust makes sure it never is.
Just going back to your point there, Richard, about other types. So just to quote from the book, so variance is the reason why in Java you can pass a turtle to a function that accepts an animal if turtle is a subtype of animal, or why in Rust you can pass a ref static string slice to a function that accepts a ref tick a string slice. So it's exactly the same concept. He does call it out. I should have mentioned it in the slides, because the words didn't mean a lot to me out of the context. I was like, I'm just going to talk about the context of lifetimes.
The word subtype confuses me sometimes, because subtype seems to me something smaller, but really in lifetimes it's a larger lifetime.
Yeah, exactly. Yeah.
In objects, it's the same, right? But really, the lifetimes are a part of a type, right? In Rust.
Yes.
And that much is exactly what it is in C++. It's just C++ doesn't consider lifetimes at all. But it's a type, right?
Yeah.
Wait, how are lifetimes types? That would imply that one type can only have one lifetime, right?
No. So you have a type, but because of lifetime, you have multiple types of the type.
It's not a concrete type in the same way that it is. So it's something that's derived at compile time, but it's associated with the type.
It's very similar to
associated
templates.
with the place.
It's very similar to C++ templates, where you have values or types associated with another type in generics, right? This is just another kind of thing that's associated with a type. So when you create a reference, it has a lifetime associated with it, and we use the tick notation to say that these lifetimes need to be compatible. I can have this lifetime from this reference and be the same as this other lifetime from this other reference, because they both share tick A.
And
right?
compatible, but not the same, which is why this idea of covariance becomes really useful, which is why you can, if you've got a function which returns a reference, and that reference is some generic parameter tick A, you can still return a static reference in that case. As long as it lives as long as tick A, then it will still be valid. So although it is tied to the type, it's not it's not like an exact, like this is exactly what the lifetime is, if that sort of makes sense. That's why it's always a generic parameter. It's never it's apart from static, it's never like a concrete parameter. Does that makes sense. Someone put a question, we'll come back to the Q&A, but just someone put a question about, did you mention when the next occasion will be? Sorry, put a bunch of links of like useful resources if any of the stuff in this didn't make sense. Particularly really like the Polonius talk, talking about like next gen borrow checker, which is really good, just about explaining how the borrow checker works now as well. But the upcoming meetup, so Matt's going to cover the next chapter on the 21st of February. So because in 2 weeks is Valentine's Day and we thought people might not come, we've done it for 3 weeks this time, but then we'll try and get back to the 2-week cadence after that. We would love to have some people volunteer to present the next chapters. I'll put out a poll when I get a chance to write one, probably tonight and or tomorrow, and post it on the Discord. But I also wanted to call out, I got a message from Phil Nash asking if we would tell folks about C++ Online 2024. So I, of course, would love to tell you guys about it. There's an online conference happening. This is what it looks like. And we might be able to get discount codes for our Meetup members. I'll let you know if that happens. But yeah, FYI, that is happening. But in terms of our stuff, this is the main things we have scheduled. Mainly book club stuff for now, but we do have some non-book club talks coming up in the future as well. So yeah, watch the space. We'll post them on Meetup and on Discord. Okay, back to Q&A. Any discount codes for the book? That's a good question. I don't have one. I can ask. I can see if we can get one. Yeah, it's a good point. I'll ask. Currently, no. Someone says, if a reference is a type, then constraining its lifetime, I guess, makes it a special reference. This is a type. The lifetime is part of the type. Oh, sorry, I see what you mean. You're saying the reference is the type, and then the lifetime is part of the reference. Yeah, you could think of it like that. Yeah.
All references are associated with a lifetime. There is no such thing as a reference without a lifetime.
Maybe I try to, like, what I have in my head to explain that. Like, I was always thinking, like, these references, they have like implicit lifetimes. And if they are like implicit, every reference like introduces a new type that is used internally by the compiler to make all this reasoning. And you as a developer, you also have like the capability to opt in to give these lifetimes names and then describe how they are interacting with each other when you have like like two references that have like the same lifetime A, so they have to live the same time, right? And actually that I think it makes it quite hard. It makes it convenient to code because it's often him, but it's quite hard to understand if you try to dig into it.
I always thought lifetimes are similar to functional programming monads, so difficult to explain. But once you get used to writing code with dealing with lifetimes, it does get a lot easier, and you do instinctively understand what's going on, because you start recognizing these problems. If you ever use other system programming languages like C or C++, you recognize the problems that lifetimes are avoiding, because by using those languages, you hit them all the time. It's just been formalized in Rust. But I said it like,
the nice thing about references in Rust is the fact that if you're just dealing with one, just one on your parameters, just one on your return type, then yeah, it's elided. You don't have to think about it. And when you're passing multiple, it totally makes sense to have to specify which one it's tied to. Like if you're returning a reference, that reference has to come from somewhere. And if you're storing a reference, that reference has to have a lifetime. It has to live a certain length. So conceptually, it totally makes sense to introduce this concept of explicitly tying stuff together. And I think the reason you then have to write it is that the compiler only has visibility. I think of it as a compiler only has visibility to like the function signature and the call site. So it's not traversing the entire tree as far as I'm aware to go into the method. So you have to make sure that your function signature is enough to tell you what the call site can do with the returned reference. Justine got another question. Any plans to have a practical project developed while going through the book? That is a really nice idea. We've not done something like that before. If you have any ideas for like what would make a nice project, that's always the tricky bit, is thinking of something. I think it maybe will be easier as we get past the first 2 chapters, because the first 2 are like all the fundamentals and then move on to the bigger stuff. But we definitely can try and do that. It might be helpful for like collecting together examples and things. Yeah, any suggestions? Just, yeah, we can try. Or you can build a project and present on it alongside. That's also totally up for grabs.
If I may hop in, like, to do a bit of advertisement, I kindly ask. So like I'm working on a video series. It's called Pragmatic Rust for Engineers. And yeah, so it's not too much related to the book. And I actually think I'm quite also kind of a learner, because I have most experience in C++. And I actually run into ergonomic problems with lifetimes when using another crate. And with generics, I just would love when people check this out. There's a nice project. We are like simulating a reactor with multiple beds, which are parts of a pipe. And yeah, yesterday I was recording like clips for the third video, where we built up a WebAssembly tool that enables like a user to change the temperature of different pipes and see nice plots in it. So maybe if you're searching for like learning materials that are oriented on projects, maybe give it a look. It would be great.
Do you
Looking
want to
for
drop the
feedback.
link, Tim, into the chat
Yeah,
and into the Discord as
should.
well?
Ciara,
Hiya.
can you switch to the page with the links again for a moment?
Oh yes, yeah.
Please. Thank you.
This one, yeah. Sorry, I can drop them in the chat as well. That's probably easier for people. And just in case anyone missed the book itself. Oh, many slides, too many slides. And don't know why I didn't link it in this one, but Jon Gjengset, the author of the book, if you haven't seen his YouTube channel, if you search Crust of Rust, he does this series of like kind of specific topic ones, but then he also does these live streams where he just does stuff and shows you it and talks through it, and it's really great. Yeah, the short video is like a good introduction to his stuff, but super smart guy and very like free sharing with his knowledge. So it's not, there's one of the reasons why I think it's good if you can buy the book is just to support him, because I think he's a great developer, but he's also got
he's really cool, and he actually encouraged me to like start this project. Like I was thinking about it, and he gave like the final push. He was really encouraging guy.
He's really cool. He gave us permission to do this in the first place. Ciara was good enough to ask permission before we started this, and Jon said yes, which is amazing if you think about it, right? So I love watching Jon's videos. Some of the videos are quite long, so you have to put aside 2 to 3 hours to go through them. But by going through them, you get so much practical experience of dealing with Rust and seeing his mistakes and seeing how he solves them. It's very valuable.
All right. Any more questions? We've got, a few weeks before the next meetup. So if you've got any questions about just the meetup in general, this is I guess this is now free for all chat for the next like 5 minutes, or however long people stick around for, until we regroup.